Class, we're going to start studying Chapter 2, and one of the main things that we'll talk about is tomorrow is looking at ways that we can describe individual points in a distribution. We spent a lot of Chapter 1 talking about distributions, shapes, and measures of center and spread and those kind of things. So we're going to go a little bit deeper with some of those ideas in this chapter. One of the questions that I usually start with, and I've not done the video for this before, but I'm just trying something a little bit different this year. Usually start with this question. I'm a big baseball fan, especially now in the playoffs and whatnot. But three landmarks of baseball achievement are Ty Cobb's batting average of 420 back in 1911. Ted Williams hit 406 in 1941 as the last person to actually hit 400 in a baseball season. It's been a long time. George Brett came pretty close in 1980 when he hit 390. So the question is, which of those is the most impressive? Batting average is essentially a percentage of, by and large, the number of times that you got hits divided by the number of times that you were at bat. And so the higher that number, Ty Cobb, for instance, got on base by hit, 42% of the times that he went up to the plate, which is a really remarkably high number. But which of those is the most impressive? And as it turns out, you really need to have some sort of background, contextual information to be able to make that decision. So we're going to kind of further develop this idea tomorrow. So we're going to go back to this slide and just kind of fill in some of the notes here. So the first thing we're going to talk about is how to measure a particular position within a distribution. And there are two main ways to do that. One way, of course, is with this idea of the percentile. Our formal definition for this is that the p percentile of a distribution is the value with p% of the observations less than it. So, for instance, a lot of you have probably seen things like percentiles before with standardized tests. If I'm in the 92nd percentile, that essentially means that I scored better than 92% of the other people that took the test. So percentiles are really good ways to kind of give you a sense of where you are with respect to everybody else. So that's one of the main uses of percentiles for real large data sets. So that's all about percentiles. Some books, by the way, will also say things like it's the percentage of observations that are at or below a value, but we're not going to use that. We're just going to look at the ones that say less than it. And that's kind of our working definition with our textbook. And that will be consistent with what we talked about in a little bit. The second thing I want to talk about, the second main way to measure a location in a distribution is by looking at what's known as the z-score. And the z-score is defined as follows. If x is an observation from a distribution that has a known mean and a known standard deviation, then we call the z-score the standardized value of x. Okay, and so the z-score is essentially given to us by this formula that's shown. We take the individual observation and we subtract off the average of the data set. So this, we talked about the other day, this is just the deviation. How much does the individual data point deviate from the mean? And then we're going to take that difference and divide it by the standard deviation of the data set. Okay, so a conceptual understanding of what that is, the z-score just tells us how many standard deviations away from the mean the data point is. So by the way, I failed to mention this, but I did give you a blank copy of these notes during class today, so you should be kind of filling those in as you go. And if there's a place where I said something that doesn't quite make sense, or you want to kind of talk about it a little bit further tomorrow, please just pause the video and make a little star or something, or a little note to yourself to ask those kind of questions in class tomorrow. So we can definitely do that. This just kind of frees up a little bit of time for us to be able to do some other things. So back to z-scores. So how many standard deviations, the point is, away from the mean of the data set. And so a couple of conceptual ideas along with that would be that if z is positive, that means that my score is actually above the mean of the set. And if you think about that in the context of this formula up here, if my value is positive, that means that my number is bigger than the mean of the set, right? Which gives me a positive numerator in that fraction, and then I'm dividing that by a standard deviation, which is always positive. Standard deviation is always positive because of the mathematics that we did the other day, but also conceptually, remember that standard deviation is it's an average distance of the data points away from the mean of the data set. So since it's a distance away from the mean, then that number is always going to be positive. So that makes sense also, like conceptually. Okay, so z is positive if we're above the mean, and then likewise, conversely here, z is negative if it is below the mean. So the positive z-scores means we're above average, and negative z-scores means we're below average in terms of standardized scores. All right, so the next slide gets into an idea called cumulative relative frequency. We're given a data set here, at least a partial data set, table showing the distribution of median household incomes. So median household incomes for the 50 states and the District of Columbia. Oh no!
Chris Rossetti, please dial 2000 or come to the main office. Chris Rossetti, please dial 2000 or come to the main office. Thank you.
All right, so our first task here is just to determine what relative frequency means. What is cumulative frequency and what is cumulative relative frequency? And then we're going to finish filling out the table. Okay, so essentially this table is set up like this. This first column here with the median income essentially is saying that 35 inclusive up to $40,000 a year. It's saying that there is one state, it could be the District of Columbia, but one of those 51 entities that has a median household income somewhere between $35,000 and $40,000 a year, inclusive of $35,000, not of $40,000. So the frequency is just another way to talk about the count. How many of those things fall into that given category? In fact, we can take the first two columns of that table and just make a histogram out of it. Okay, which each of the bin widths would be 5 wide, and we'd have a histogram that kind of shows us that distribution. Relative frequency is essentially turning the frequencies into percentages, and so that's a pretty easy thing. Since there are 51 states, including the District of Columbia, then we just divide the number, or the count, divided by the 51 total entities that we're talking about there. And so the relative frequency that's a really fancy statistical way of just calling it the percent. Okay, so cumulative frequency is a little bit different. It's based on these other numbers, and as you can probably see from the table, there are a couple of different ways we can arrive at that. Cumulative frequency, much as the name would imply, it's like it's cumulatively, it's adding up to that particular value. And so when I look at this number, for instance, this 11, cumulatively up to this point, up to 40, but not including 40. So if I'm looking at this bin width here, 40 to 45, and this is essentially saying that there are 11 states that have a median income less than $45,000 a year. And likewise, this 25 is adding all of these categories together. Cumulatively, if I add 1, 10, and 14, that tells me that there are 25 of those states that have a median income below $50,000 a year. And so that's what cumulative frequency is. And then when we put this word relative in here, all we're really doing is turning those cumulative frequencies into a percentage. And so, again, taking those counts of the cumulative frequency, dividing by 51, and we're getting percentages for those. Not percentages, but proportions, I guess, formally, but roughly percentages. Okay? So what I'd like for you to do is to take a minute and pause the video, and I'd like you actually to take a second to fill out the table and kind of make sure you work through those numbers. When you get done, this, by the way, should be 1.00 it's, everything has to be below that $70,000. That's the highest range that we have there. So take a second to do that, pause it, and then we'll take a look at the answers here in just a second. Okay, so here's a completed table, actually. And so what we have here is the same basic thing that we started with, except this has all just been completed. These last two columns have all been completed. And so that's essentially our table that we're working with. Now, cumulative relative frequency, by the way, is another fancy way of saying percentile. The way we've defined it makes it and cumulative relative frequency the same thing. Because if I look at this number right here, this 0.216, I could say something like, 45 is the 21st percentile, something like that. There are 21.6% of the values that are below $45,000 a year. So in that respect, it's the same thing as percentile, just being called a different term. Our friends in IB call these ogives. Ogives actually derives from some. I didn't do that well. Sorry, I'll go over that. Ogives. Ogives is derived from the term from about 150 years ago when these ideas were developed. Ogive is actually an architectural term that describes a certain shape on a building, which we'll talk about when we get to the graph. But we call them in AP, we call them cumulative relative frequency. Much less pretty to say, but it kind of refers to the same thing. Okay, so that's our completed table, and hopefully you're able to come up with that on your own. So the second part of this slide is we're going to make a cumulative relative frequency graph. And the way that we do that is it's kind of like almost like an XY coordinate plane kind of thing. And so what we're going to do is we're going to put cumulative relative frequency over here. So that last column essentially, and that's going to go from 0 to 1. So we'll go ahead and do that here. Whenever you make a graph, make sure you're labeling what's being shown there. Make sure you're putting a scale that represents what's being shown. Then we're going to put the median income on the horizontal axis. And we'll just sort of shortcut this by saying in thousands of dollars. And then there, maybe we'll put a little break in our graph here, maybe start at like 35. We want to make sure that we have a hatch mark here at each of the category breaks. So we'll count up by 5,000. So from 35 to 70, that's what our table would have us at. Okay, so now the idea here is we're basically going to take these points from up above and we're just going to create some data points from them. And you kind of think about this in terms of a percentile. So what we want to show here is the cumulative relative frequency as it relates to the individual median incomes. And so what we always want to do here is we want to sort of start here. We want to maybe like even pretend like there was like some category up here, 0 to 35 inclusive. 35 is going to be at the 0th percentile or have 0% of the data points below it. So we're going to have a data point on our graph that is literally at 35,000. It's going to be the 0th percentile or have a cumulative relative frequency of 0. And so we'll come down here and we'll graph that point right here. That means 35,000. There are no points below it. And we kind of do the same thing here with the rest of the data points. So our next one, and depends on how you want to sort of think about this, but we take this value here, this 40, and 40 is actually at the second percentile. 2% of the data points are below 40. It really represents just that single state that has that lower median income. So we're going to have another data point that's at 40 in the point 02, the percentile or the cumulative relative frequency at that spot. It's probably not going to be able to show up a whole lot here, so it'll be a small increase here, 0.02. Notice not 0.2, 0.02. I'm just going to kind of continue that idea across the board here. So 45, the value of 45 is this. That means that they're 21.6% of the data points are below 45. Okay, and we're just kind of continue that here. So what do I have here? 45 and 21.6 is about right here. Just go ahead and put those other points. I'll just list those over here, I guess. So we have 50, and that's at the 49th percentile. We have 55, which is at the 72nd percentile. 72.5%. 60 is going to be at the 0.824. 65 would be 94.1, 0.941, and the value 70, there's nothing above 70, so that's going to put us in the 100th percentile. 100% of the data points are going to be below $70,000 a year. And we'll just take those down here and plot them accordingly. So we have 50 and 49, it's kind of a big jump there. And we have 55 and 72.5. Starts to tail off a little bit. 60,000, 82.4, 65,000 and 94, and then finally have 70 at the 100th percentile, or 1 on the cumulative relative frequency graph. And then we just take those values and just kind of make a line out of them. I'll probably use the same color. Okay, and so you'll notice here that this is actually where the name ogives comes from. There was an architectural, like a corner of a building or something, like the edge that kind of took on this basic shape of what this graph actually looks like. That's where the name ogives comes from. But it's just a nice visual demonstration of what that graph actually is, and how the individual values compare to the percentiles or the cumulative relative frequencies. And so some of the things that you might notice here is that the steeper the line, this part right here is really steep. And think about that. Essentially, all that means there's a whole bunch of data points that are in that point because it's causing such a huge change in the percentile. In these 5,000 values between 45 and 50, that essentially is containing. It looks like about 30-some percent, right? It's a pretty big jump there. 30, yeah. So quite a bit of a percent. So the steeper those lines, that means the data is packed together a little bit more tightly. So there's some conceptual things you can pick up from that. Let's do a couple follow-up questions, and we'll be done here. So let's get rid of those and come back down to our questions here. So we're going to use the graph for the state income data to answer each question. At what percentile is California? California has a median income of around $57,000. And so what we would like to do is to use this. And there, this is not like the perfect scenario because we're kind of smoothing out some of the things here by just looking at those individual, 5,000s. We're only doing increments of 5,000. But if I come over here to 50, about where 57,000 is, sort of draw a line up here, and then sort of take that across to the other side. It looks like I'm about at the 80th percentile, so a value of 57. We don't know this for sure, but the best that we can really tell from the graph is that California would be at about the 80th percentile. And so be kind of vague about the way we say that. It's about the 80th percentile. And lastly, estimate and interpret the first quartile of this distribution. Okay, so this kind of ties together some things that we talked about in the last chapter. Remember, the first quartile really just separates, literally the first quartile is the median of the lower half of the data set, which essentially means that it cuts off the bottom 25% from the rest of the data set. Okay, and so when I look at that's really what that means. The first quartile is the 25th percentile. 25% of the data is below that value, roughly speaking. And so we can also do the same kind of thing for using our graph, but kind of using it backwards from the way that we used it before. And so if I come over here to 25, we might put that about right there, draw that down, and roughly about $45,000 thereabouts. Okay. So this is roughly equivalent to about $45,000. Make sure you're putting units on these things. About $45,000. It also says to interpret what the first quartile actually means. And so just to finish up, we would say approximately 25% of all states have a household median salary. Make sure you always put context in here. Have a household median salary below $45,000 a year. Okay, that about does it. So again, if you have any questions about anything, make sure you make some notes of that. We can talk about it a little bit in class, but this will kind of cut out a little bit of time in class today, or tomorrow rather, so that we can kind of work on some problems together, maybe do a quick data collection activity. So thanks.